you. So, uh, so in the last few classes, we had discussed X-ray diffraction. The different aspects of X-ray diffraction was discussed, and so we learned about the Miller indices. That's the starting point. Actually, when you start describing the X-ray diffractogram, try to understand the lattice planes. First thing is that you should know how to uh, assign the planes, their indexing, how the indexing is done. Then the directions, the crystal direction, that is the perpendicular vector that you uh, perpendicular to a set of parallel planes. So that crystal direction is important. So we were also able to relate the d values, the d interplanar spacing with the HKL. Then the d value was also correlated with the lambda, that is the Bragg's condition. So all these things you know, and if a numerical comes based on that, or any such question based on Bragg's equation, d related to HKL, finding the HKL of a given system, so those things you can do. This is what is expected out of you uh, when you okay. So that was the previous things. We discussed the patterns, powder XRD and single crystal XRD. So basically, the story of the missing line. So if you solve that assignment that I had given you, then you will learn why you are getting less intensity in NaCl here, and at the same point there is absence of. So this thing you will get in KCl and NaCl, why it is like this. So these two things you will learn when you solve that assignment. uh, that NaCl picture that I have shared with you, the crystal lattice with the different coordinates, and then you substitute there f plus is equal to f minus, so certain lines will go missing. Wherever there is a f plus f minus term is appearing, there will be reduced intensity. So 1 1 1, whenever you have odd numbers, you find over there, when you solve that problem, you'll find that whenever there is odd number in FCC lattice, this kind of thing, then there will be reduced intensity at that point, because f plus f minus subtract. And then if f plus f minus happen to be equal in strength, then it is cancellation will be zero, intensity will be observed. So that's why KCl. So write that 27 terms in the, write an equation where 27 terms will appear, and then you try to solve that. So this one needs to be solved for that. So this question that I had given you, so you take the hints and try solving this equation. Write the 27 terms of the equation, 27 lattice points, so 27 terms, and assign the, so if scattering factor will be halved if they are shared by 2, 1/4 if it is the edges. So this one, so this will be 1 by 4 if this, the corner ones will be 1 by 8 if, okay, and the face ones will be half if. So those things, so you do that and then use this equation. E to the power I pi is -1, cos phi is this. So convert everything into cos theta relations in form of cos, and find what you are getting, and then substitute. Then think of k plus and Cl minus. In that case, f plus f minus will be equal, and then you see, you by yourself you will learn that certain lines will have zero intensity. Okay, so solving that problem is the key. Now coming back to this X-ray diffraction, uh, the instrumentation part that I was discussing earlier, I told you that how X-rays are generated, and that was, if I go to the previous slide, you can see that I told you the generation of X-rays is done through this in a typical setup in a laboratory frame. It is done by heated filament. It is a discharge tube uh, where, so in vacuum you have this heated filament of tungsten, which here the filament is heated and the electrons travel hit this target, which may be copper, tungsten, in vacuum, and then these red lines indicate that X-rays that come out from that surface. So all those things were discussed earlier. So so here, depending on the target that you have, you can have limited range of X-rays. The intensity usually, so this is common in the uh, X-ray diffractometers that is available in laboratories, in universities, and everywhere. That packed system that you, compact system that you have. But sometimes it is the X-rays, you might think of having X-rays of different wavelength, and that is may not be possible to do with this particular system. Then we need additional sources of X-ray, and for that we have to rely on something called synchrotron. Synchrotron is a setup which is very very big, huge. I mean, it's almost a kind of you have a football field or something like that, you can say. So there's a huge infrastructure, and it is always created at a national level or international level. So at national level, we have synchrotron radiation facility at in Indore, Center for Advanced Technology, that comes under Department of Atomic Energy. Similarly, you have one in Italy, where worldwide people go for synchrotron radiation studies. So synchrotron radiation is what is this? You have, so in this, what happens is that you have electron beam. So you have electron beam which moves through, which is first the electron beam is generated, and the electron beam then is made to pass through a series of magnets. So these blue squares that you see, these are magnets uh, arranged in a circular fashion. So what happens? The electron will feel the magnetic force and it will bend along the path of this. And so as it bends, there is acceleration. So in a circular frame, whenever you are moving, it is always there's change in direction, and there is always acceleration happening. And in this case, any accelerating particle will generate radiation, lose some energy in form of radiations. It will so this is a Maxwell theory that is utilized here. uh, and so these green lines that you see, it is the radiations that come out from this set of arrangement when electron is forced to move through this system network of uh, these magnets, which are arranged in a big, say you have a big field like structure. So that's a facility, kind of facility that is needed to generate this kind of. But in this case, the advantage. So these are the X-rays. Just a moment. So all these things that we see here, these are X-rays. We also call it synchrotron radiation. These are the same thing. Uh, so these X-rays are generated, which are much more intense, and you can get of different frequencies at controlling the speed of electrons in the beam. You can uh, calculate. You can get different wavelengths. So this acceleration leads to, so these electrons are accelerated close to the speed of light in a storage ring. That's the idea. This storage ring comprises of this an array of uh, magnets. So so this is and they are several orders of magnitude more intense than the any laboratory sources of X-rays. So that is the advantage. Sometimes your laboratory X-ray diffraction may fail because the sample requires intense source of X-ray, slightly different wavelength, but in those cases it may fail. So there comes the need for these synchrotron radiations to have certain. So this is always a national or international facilities, much because of its size. It's a huge size. It has to be set up with permission from Atomic Energy Commission and all that. So lots of uh, things are involved here. So basic idea is that electrons undergo acceleration, and accelerating electron will lose energy and give out radiations. So that is X-ray, and this X-ray is what gives you. So this X-ray is then used for pass through the crystal to, and the diffraction pattern is obtained. So this is so the signals are much more intense when you do with a synchrotron, but it is one in one country it might be one or two facilities, something like that. So so here the advantage is also that you can do smaller samples and crystals, such as a 10 micron can also be used. But in that case, so uh, so this is the advantage of this kind of setup, where you can smaller samples, smaller crystals can be taken, and you can still get the good data. And further, it will also help you in taking biologicals like enzymes. They're very difficult to do. The X-ray diffraction of proteins and enzymes is difficult, and so such complex structures you need synchrotron radiations. So many biological structures, uh, if you want to study through X-ray diffraction, then it is this thing that will be required. So synchrotron source, X-ray beam from synchrotron, that is made to pass through the sample, and the diffraction pattern is obtained, and then on so this pattern is then further analyzed through the algorithm set that has been set, and you on the screen immediately you will see a kind of profile for the intensity versus 2 theta. Okay, so X-ray diffraction, so lambda of this wavelength of zero point 0.3 angstrom is used here. So you can get shorter wavelength, much shorter wavelengths here. I told for copper, I told you that if you have a copper K alpha, the wavelength is 1.5 angstrom. Here you are getting 5 times smaller, uh, shorter, 5 times shorter wavelength when you are using synchrotron, and that is you are using a much higher energy X-ray as compared to that typical that one. So it is more intense. Intensity is more. The wavelength can be adjusted. So this is the advantage of us typical synchrotron based X-ray diffraction. Now we talk about the neutrons. Neutrons again have both particle like dual behavior. So de Broglie's uh, equation is you can apply and you can get the wavelength, and for so what are the properties of, so basically neutron has certain mass, that is it is almost around 2000 times more massive as compared to electron. Zero charge, but it has spin half, and that's why, because it has spin, I told you anything that has spin will be magnetic, so it has magnetic dipole moment. And that's a advanced quantum mechanical concept where spin, if anything, any fundamental particle having spin will be magnetic, it will have magnetic dipole moment, and that magnetic dipole moment is this mu n. So uh, so uh, so yes, when you are talking about, so this is the particle nature that you are talking about. If you want to talk about the wave like property, we talk about the wave vector or wavelength. So that also you can calculate using the de Broglie's equation, and then you can practically what we find that, so neutron, if you need neutrons, what is the source of neutron? It is always a nuclear reactor. It is a nuclear reactor. So if you want to do something studies on neutron based studies, you have to go to Bhabha Atomic Research Center, where you have nuclear reactors are there, research grade nuclear reactors are there, and some neutrons will be produced in the fission reaction. Fusion is in a controlled way is not yet done. So in fission reaction, nuclear fission will lead to generation of neutrons, and those neutrons can be if their wave-like behavior when we analyze, they can have the wavelengths comparable to the separation between the atoms in a crystal. So at that point, the criteria for diffraction is satisfied, and we might get diffraction pattern. So you have neutrons classified into three different categories based on their energies: cold neutrons, thermal neutrons, and hot neutrons. So you see the wavelengths here: 0.4 to 3 nanometer, zero point 0.1 to zero point 0.4. So this will suit you. 0.4 1 nanometer, that means 1 angstrom to 4 angstrom. So this might suit you. So usually this one is the most suitable one. It has so with 5 to 100 MeV, and so you can calculate if you know the velocity, you can calculate the lambda wavelength associated with it by using this formula. That is, you can also arrive at this formula very easily using the de Broglie's equation, and so putting the substituting for mass and everything. So this is the wavelength that is suitable for performing suitable for diffraction through a crystal lattice. Okay, so almost if we put it in angstrom, it is 1 angstrom to 4 angstrom. So that's the range. You have the atomic interatomic distances in the thing. So these are moderate electron thermal neutrons that which have energy on the order of room temperature. So that is when we call them thermal neutrons. So they are on the order of energy is on the order of kT, and that's why we call it thermal neutrons, and this will be useful for. So in 1994, Nobel Prize was given to Schill and Brockhaus for this discovery, uh, that neutrons can be used for diffraction, and it can be used for diffraction studies. And through this diffraction, you can get to know about the crystal structure, not just the typical ionic crystal or silicon semiconductor crystal, but also the biological samples, which are rather difficult to perform by X-rays and other things. So sometimes, so neutrons are very useful that way. So this is what happens. You have a reactor, nuclear reactor. So nuclear fission in the reactor. From a nuclear reactor where fission fission occurs and neutrons are generated. This neutron beam is then passed through this a crystal, which separates. There will be different neutrons of different velocities, so it segregates them, and a proper wavelength and a proper so it acts as a filter. It doesn't allow certain neutrons of the certain energy to pass through, and only so you select something and let it fall upon the crystal, so it is a crystalline sample. Then these neutrons, the green dots that you see, this is the neutron beam that is getting deflected, that is getting scattered, and here is the detector. So the detector, when it undergoes elastic scattering, you get collect these signals, and then accordingly detector will give you signals intensity at different angles, different 2 theta values, what is the signal intensity, and that we analyze and get to know about things. So this is what happens. Three spectrometer is there. So the spectrometer, in the spectrometer, the sample chamber is such that the crystal is rotated. Crystal is rotated, and this is, on rotation you get 2 theta value will change, and so one by one you can get a different you can get the different at different 2 theta values you can get the signals where the this constructive interference occur, they will get the signals. So that is how the signals are collected. Energy of the beam that is analyzed through another set of crystals here. So neutron is get counted in the detector, and that's how you have this thing happening. Okay, neutron beam. So this is the basic idea. So diffraction occurs through crystals for any particle with a velocity. So these de Broglie relation, if you know, so what the basic idea is that you have to get those neutrons which have if you calculate their wavelengths, they must be comparable to the atomic separations, atoms separation of atoms or ions in the crystal. So that criteria is met, then only diffraction will occur. So that is so once you have done uh, so usually neutrons that traveling at that is 100 200 picometers, so that comes out to be 10 to the power picometer is 10 to the power minus 12, so it is about 1 angstrom, or so this is equivalent of saying that we are talking about 1 to 2 angstrom, and thus undergo diffraction by crystalline organic compounds. So this is the separation, and that's good. Neutron beams of appropriate wavelengths are selected, generated by the. So it is generated by what? Nuclear reactors, as I told you in the previous. So you need. So this is why nuclear reactors. So neutron diffraction can be performed in only in specific places, and it will again be a national level, international level center specifically made for research grade nuclear reactors. Okay, so that is so there. So this is the common thing. If by fission nuclear neutrons can be produced. However, there is another method called spallation, which through which uh, neutrons of certain of this particular energy can be generated. So this is spallation is an example, but this is involves a particle accelerator. So it is a slightly smaller setup as compared to nuclear reactor, but still it is accelerator is always also a big, relatively bigger, around the size of a room or two rooms, one, two, three rooms like that. When you see in the so that kind of this thing is particle accelerator, a long pipe like things where the particle gets accelerated. Some so and that the technique that is involved is that spallation. So it is a violent reaction which so you have a target nucleus. So this is the target nucleus, and this is the energetic proton. Sorry, so this is the target nucleus actually. Uh, this is the target nucleus, and this is the green dot that you see is the proton, energetic proton, and when this green dot hits this target nucleus, it is it it gives out it becomes unstable and gives out some of the neutrons. These red dots that you are seeing is the neutrons given out in different direction. So this is a typical uh, this is a process which is called spallation. So typical example of a spallation is shown here. So in this so it is by disintegration of the nucleus, target nucleus, you are generating nuclear reaction. You are generating the neutrons, which can be used for studies for investigating the crystal structure of anything. So protons, neutrons, alpha particles all are generated, but you can collect neutrons and make it pass through the so again you need to satisfy the Bragg's condition for the diffraction to occur. So lambda must be on the order of separation between the atoms in the crystal. So instrumentation used are similar to what we did, and the pattern that will be obtained will be also similar for neutron diffraction. Uh, However, the scale is much larger. That is to say that you can go to a much greater depth. If you have a very thick crystal, layer by layer structure of different materials, so that kind of structures can also be analyzed in a much better way, because penetration depth is good. X-rays are, as compared to neutron, is, a neutron beam is highly penetrating, and that's why we are able to, if we use neutron beam, will it will penetrate through layers of the atoms and reach to a greater depth. So you will be able to know the smallest, if there is some impurity, or if there is something, uh, different types of atoms present in the crystal lattice, that can be very well understood. So that is because of the, so again, neutral only is few places in the worldwide you can perform neutron diffraction. So that's why it is a very rare thing. We in India we have neutron diffraction center only in the BRC, Bhava Atomic Research Center. But it has several advantages over X-ray diffraction. And sometimes when X-rays diffraction fails, then you go for neutron diffraction. Uh, so it is less routine and limited to less limited. So X-ray cross section. So X-rays, as we learned in the previous classes, X-ray scattering happens. Basically, it is the scattering from the electrons. It is, so as the atomic number increases, number of electrons increases, and so for X-rays, you find that bigger is the atom, heavier is the atom, the greater is the scattering from that center, because number of electrons increases. So hydrogen is the least, scatters the least. If you pass, if you have in your sample crystal lattice, if you there is hydrogen atom present, then you won't get any signal from that. So it is difficult to locate its position in X-ray. So think of a metal hydrides. uh, so metal hydrides, if you think of metal hydrides like sodium hydride or any other heavier cesium hydride like that, or for that matter lead hydride. So in these cases it will be very difficult to know the position of hydrogen, because the scattering intensity, hydrogen has, hydride ion will have only two electrons, and that will be, so H minus is the hydride, and so there will be hardly any signal from that atomic center, and so it will be difficult to locate that hydrogen atom in the crystal, hydrogen hydride ion in the crystal. So there you have failure of X-ray diffraction in locating the hydride position, because the scattering is less. But at the same time, if you analyze this part, neutron cross section, the scattering of neutron from the same point, hydrogen very very good, a bigger cross section. So many lighter atoms like deuterium, carbon, and others, you have this kind of thing, that you will, which is good. So lighter elements also have a very good cross sections of scattering, scattering cross. So more, so that helps when you have a combination of a very large atom combining with a very small atom. So hydrides was the situation where lead was a very big atom, hydride is small, an ion. So how will you get the position, get to know about the position of hydride in the crystal? So that is the problem, and that is resolved when we use neutron diffraction as the technique. Then we are able to know both the positions. So this scattering is different, it occurs, and it is not the electrons. When we are talking about neutron diffraction, the scattering occurs through nuclei, the heavier atomic cores, and not electrons. So it is not unaffected. It remains unaffected by presence of electrons around the nucleus and hits the nucleus, and from there it gets scattered. So that's why we have this kind of different behavior, scattering. Neutrons are scattered by the nuclei and not by electrons, because electrons are much lighter, and so most of the scattering occurs with nuclei. So it finds so it is very sensitive to the structural changes within the crystal, and sometimes it will give you a lot more information than the X-rays. Uh, so scattering is not X-ray scattering is always dominated by heavy elements. X-ray scattering, X-ray diffraction will be always dominated by, you will get greater signal from the site of heavier atoms, and so X-ray diffraction suits most of the things. But whenever you have a lighter element being used, like hydrogen, lithium, in that case, these lighter elements are particularly in combination with a heavier element like lead, then it becomes impossible to get the uh, structure of uh, structure of these crystals by X-ray. Okay, because you are not able to locate the anionic these centers of hydrogen or lithium. So almost all the electron density will be due to the lead atoms. In this case, if lead is present in combination with hydrogen, and so it is difficult to get to know the position of both the atoms. So with neutrons, lighter and elements, lighter atoms can also be uh, they have also have higher scattering cross section, and this intensity is significantly enhanced, and so for metal hydrides it is particularly suitable when you have heavier atoms combining with a hydrogen like small atom. And similar is the case with lithium or oxygen. If you want to produce, it is always much more uh, better to use if you have, even in oxides. Yes, oxygen versus a heavy element, heavy metal oxide, you need to do neutron diffraction to get to the position of oxygen. So, uh, so this is the yeah, this is one of the advantages, a big advantage in that sense. So the typical study hydrides and metal oxides, uh, particularly for these things, you will get some more information, better information from the neutron diffraction studies as compared to X-ray diffraction. Uh, so in some cases, like designing of superconductors, it is very important to locate the oxide position in the crystal. Okay, with in association with barium and thallium. So. So sometimes you need to and hydrogen atoms position also. So in those cases you will have to do neutron diffraction. So it's not just academic studies why we are locating the atoms, so interested in locating it, but it's also the application point of view which uh, which takes you to that point that neutron diffraction is better suited. It will also be better suited in case of isoelectronic species, nearly isoelectronic or some. So if you have nitrogen and oxygen present simultaneously in a crystal, it will be very difficult to know their positions in X-ray through X-rays, because they have same number of, almost nearly the same number of electrons. So similarly, chloride and sulfur, if they are present together in a sample, it will be again difficult. So they are nearly isoelectronic, we say. And scattering of X-ray will happen almost to the same extent. So it will be very difficult to tell the actual positions and whether both of them are present or not in the crystal. So those things. But if you do that thing by neutron, you use neutrons for the scattering, then you can distinguish between nitrogen and oxygen, because nitrogen has a 50% more stronger signal. It scatters at least uh, 50% more as compared to oxygen. And chlorine will scatter around 4 times better than sulfur. So this distinction between chlorine, sulfur, nitrogen, oxygen can also be made in a better way if these things is there. One more thing that important to note is that if you compare nuclear radiations, why so neutron is a the source of neutrons is the nuclear reaction, right? So there are several, you already in your nuclear chemistry classes you must have understood the different types of radiations that come from nucleus. So if you compare the penetration effect, the penetrating power of all these, you'll find that alpha particles have the lowest penetration and neutrons have the highest. So what does that mean? Practically what it means. So if you have a beam of alpha particles and you just put your hand, it will be stop. It will stop here. Okay. If you have a beam of beta particles, it cannot be stopped by your hand and it will travel to, it can only be stopped by a thin sheet of aluminium, something like that. Okay. If you have a gamma rays, it cannot be stopped by hand. It can also not be stopped by this thin sheet of aluminium, but will stop with a thick sheet of lead. Thick sheet of lead can stop this gamma rays and X-rays as well. Okay, but if you have a neutron, a beam of neutron, it is very penetrating. It is not stopped by human hand. It is not stopped by thin sheet of aluminium. It is also not stopped by the lead, thick sheet of lead. It can only be stopped by very thick block of concrete. So this slide summarizes the idea how the penetrating, what is the penetration effect of all these radiations that come from nucleus. So neutrons have the highest penetration power, and that's why whenever we in nuclear reactions you have, so people when they think of neutron bomb, that's very dangerous to humans. It will not damage the non-living thing, but it can only damage. So that is another thing, but interesting one, because of based on these penetration effects. So this neutrons, so in case of diffraction also, when you are trying to study a crystal which has very complicated structure, layer by layer structure, one layer of one material, another layer, second material, third material, so that kind of thing is there, then it is best to study with it is good to have neutrons. So in a because goes to a very uh, greater depth. Neutron beams can go to the very uh, depth in the crystal, and so you will get a lot more information about the crystal. So the penetration. So here it is the example of what the scattering. So uh, penetration depth, analysis of penetration. So on the y-axis you have penetration depth, on the x-axis you have atomic number. So we can clearly see X-rays are having yeah, X-rays are less penetrating for this heavier atoms. You can see less penetrating over here. X-rays initially they were penetrating. Look at this H. So they pass through this, but as the number of electron increases in the atom, the penetration decreases. Okay, so X-rays is you see if the blue line is going like this, something like this. So this is the blue curve. But and similarly, if you look at the same time the red dots, look at the red dots. These are the neutrons, scattering of neutrons that can happen through different atoms, different atoms. So because neutrons are scattered only by the nuclei, you have a different pattern entirely. So you can see clearly that hydrogen and deuterium and helium, so you have the situation is different. This is hydrogen, deuterium, helium, and this is the boron here. Boron has a low, so scattering, so penetration depth in these cases are varying, and almost it has a good penetration depth neutron across the table, except for cadmium, boron, and samarium, which are lying here particularly. So these are unsuitable for cadmium. So cadmium and boron have a, they capture the neutrons. Their nuclei captures that is known for neutron capture. You might have heard in nuclear reactors, cadmium and boron rods are used for capturing the excess neutrons. So because of this, the scattering is less, and they are just stuck over there. But if you look at the most of the elements, other elements, most of them have a very good cross section through this. It gets scattered from very well, very high cross section, and so very high. So it is reaching the penetration, penetrating the lead, elemental lead and uranium, anything. So even heavier elements, it has like lead and uranium, it has a good penetration depth. And so uh, so the signal that it is in meters. So you see this thing, this is 1 meter, this is 10 to power minus 2 meter, so like that. So the order is somewhere between 10 to power minus 2 and 1, somewhere in between you have most of the things lying over here. Definitely much greater penetration depth is there as compared to, for the same set of atoms, blue ones, consider these blue things, you have much lower, less than 10 to power minus 3 meter. So penetration जहाँ पे 10 to power minus 3 था, मतलब 1 mm, 1 millimeter था, वहीं पे अब penetration depth around few meters, less than around हाफ मीटर या हाफ मीटर के लगभग जैसा हो गया है. So that is a huge improvement, almost that kind of thing that you are seeing here. So it is almost like so what, so this plot shows you the penetration depth, and it is very good penetration for across the most of the elements, the atoms of the atoms of, through the atoms, layers of atoms of the most of the elements, and that is a very good thing. So sometimes you may not get good, so only the failure, neutrons will fail when cadmium, samarium or borons are used. Neutron diffraction, the depth is low, penetration depth is low, because these are the three things that absorb, they, their nuclei absorbs the neutrons. So that is a special property. So only in those cases it will fail. For most of it, it will be very very good. So neutron data, this is for 1.4 angstrom of wavelength neutrons. So in this same picture, you will also be able to note the difference between cadmium, boron, and samarium, which lies at the bottom of the things that already discussed. And there is no, we also find that there is no systematic dependence on the atomic number or number in case of neutrons. But in case of X-ray diffraction, you have a clear dependence on uh, like number of electrons. So atomic number dependence is all there. But in case of neutrons, for neutrons, you do not have a systematic dependence on atomic number. There is like, it is going like zigzag pattern, like this. Okay. So we are able to find the distinction between hydrogen and deuterium when we use neutron, which was never possible when, if we are using X-rays. Okay, so this is something important. Uh, so scattered with it is also, it is a point scattering, that is it is scattered with equal probability in all directions. So it is the nuclear interaction with the nucleus and not the electrical or electrical force. So in case of class नहीं करो, class चल रही है तुम्हारी,
कॉल आ गया सर,
हाँ?
कॉल आ गया सर, मेरा सर जाना है सर थोड़ा सा। जी सर, वो चल रहा है घर पे सर, फंक्शन चल रहा है सर।
किसका?
फंक्शन सर।
So neutrons, okay, so interaction, nature of interaction is, yeah, it is hits the nucleus and then gets scattered. It is because it is neutral, so neutral, so it is not electrical in nature. The interaction is not electrical, and interaction will be through via the nuclear forces. The interaction will be through these things. Scattering. So neutrons. So because they are not affected by electrons, they find, so if look at the point of view from neutrons, it finds a very empty space when it passes through the crystal lattice. It finds a lot of empty spaces and only a few centers from which it can get it can get scattered. Okay, so typically around 1 lakh times scattering center is typically smaller than the distance between two, 1000 1 lakh times small. Scattering center is typically 1 lakh times small than the distance between such centers. So two nucleus position and between, so there is almost uh, so as a consequence, neutrons, so what happens, neutron travel larger distance through the most materials without being scattered or absorbed, and then so they are less, most of the neutrons will pass through unhindered. That's what the idea is, because there's a lot of empty spaces. It is unaffected by the electrons, which is from the major space in an atom is occupied by the electrons. So it is expected that it is without being scattered or absorbed, it will pass through or travel through a large distance. So that picture on previous slides, that's okay. Later on, okay, I'll show. So what now we have is that we have already discussed the penetration depth of neutrons as compared to X-rays. In this same picture, if you use electron beam, so the yellow one, I didn't discuss the yellow ones. The yellow ones are the, so the yellow ones are the these are the electron beam. Electrons, electron beam has even less penetration. So because it is a charged particle, so it will be repelled by electrons when it enters the crystal. Each of these atoms have electrons which will repel this beam, and so penetration depth, if you look at, is very very small, much less than X-rays, and even न्यूट्रॉन के कंपैरिजन में तो कुछ है ही नहीं. सो इलेक्ट्रॉन बीम का भी डिफ्रैक्शन हो सकता है, लेकिन उसका पेनिट्रेशन डेप्थ बहुत कम होगा, सो सैंपल के थ्रू ज़्यादा दूर तक नहीं जा पाएगा. So neutron scattering is important from for one more thing. You know, neutron is magnetic. I told you it has spin while discussing bosons and this kind of thing, bosons and fermions. Uh, Neutron also has half, s is equal to half. Neutron has s is equal to half particle, so it has spin, and so spin angular momentum, and so it will have some magnetic moment, so it will behave as a tiny magnet. So behaves as tiny magnet. So this neutron that we are talking about can behave as a small magnet. And so imagine it is if it is behaves as a small magnet itself, and then it comes across unpaired electron in the crystal, it will be, there will be interaction like between two magnets, so there will be repulsion or attraction depending on their position and spins. So that can happen. So that will is an interesting point here, that by this neutron scattering, neutron refraction studies, you are also able to know the positions of the magnetic atoms. Because if there is unpaired electron, if there is uncompensated spin of the electron, you can expect, in addition to the scattering from the nuclei, you can also have scattering due to the magnetic interaction. So dipole, magnetic dipole, one magnet interacting with another magnet. Imagine electron as one magnet. So treat electron as magnet, electron as a magnet, neutron as another magnet. So north-south direction. So if so, these are two. So we are visualizing them at tiny magnets. So electron and protons. So electrons can interact through a magnetic thing. The interaction between, if there is unpaired electron, then this will happen. So unpaired electron can so neutron, so magnetic, so two magnetic dipoles interacting with each other. Remember I told you that electron behaves as a magnetic dipole, neutron will also behave as a magnetic dipole. So it is a interaction of two magnetic dipoles, and so that will also cause scattering. So so that is called magnetic neutron scattering. So if a crystal has sites where unpaired electrons are there, due to the magnetic, in particularly it happens in a magnetic material. If you can easily find the position location of the atoms, where from where the neutron scattering is happening due to magnetic interaction. So magnetic atoms can be located in a crystal, which you cannot do with X-ray, which you cannot do by electron diffraction. You cannot do by X-ray diffraction, but you can do with neutrons. So in addition to the crystal structure, you are also able to uh, quantify you are also able to know about the magnetic properties of the crystal. So it is plays a key role in determining the microscopic properties of various magnetic systems. So it is the only technique, remember, it is the only technique which can give you a magnetic excitation spectrum, complete magnetic excitation spectrum, whether the samples are dispersion form or in a powdered form. In any form you have samples, and then you can get this idea about the magnetic excitations very well. So to sum it up, we can yes we can क्लास चल रहा है, मैं बाद में 5 मिनट में आता हूँ, क्लास ले रहे हैं क्योंकि बच्चे आए नहीं है तो ऑनलाइन दे रहे थे। ठीक है क्या, पुनीत सर तो चले गए, पुनीत सर चले गए, आप लोग निकलिए। हम आते हैं। किसका, ओ अच्छा अच्छा, आप लोग निकलिए हमारे। So neutron diffraction advantages. So wavelength is comparable to the interatomic spacings. Kinetic energy comparable with that of the atoms in the solid. It is highly penetrating, very good. This is huge advantage compared to electron diffraction technique or technique. So when you have a multi-layered structure, one layer of say titanium covered with silicon oxide or something like that. So in those cases you need to know layer by layer the proper how the properties changes. So bulk properties can be analyzed at a greater depth. So it is point like interaction, interpretation of scattering data, isotopic sensitivity. So if you have hydrogen or deuterium, you can distinguish between the two through neutron diffraction. So that is isotopic sensitivity is there, which was not earlier there in case of X-ray diffraction. Neutron magnetic moment couples to B. So the magnetic field due to the, so if you have unpaired electron spins, the magnetic structure can be determined. So you can also not just the three-dimensional structure, you can magnetic structure, that is location of the magnetic atoms, what is the, and the strength of interaction, that also you can study, you can determine. So it is also possible to do it with different solvents. X-ray diffraction we can't imagine, solvent के भी तो कभी नहीं, अच्छे से सारे solvent को उड़ा के तब करना पड़ता है X-ray diffraction, but बायोलॉजिकल स्टडीज में ये काफ़ी हेल्पफुल होगा, क्योंकि बायोलॉजिकल सैंपल में पानी उड़ा तो कई बार वो स्ट्रक्चर खत्म हो जाता है, प्रोटीन का स्ट्रक्चर या माइसेलर स्ट्रक्चर है, फॉस्फोलिपिड्स का, बाइलेयर का, वो सब खत्म हो जाएगा जैसे ही हम पानी उड़ाएंगे। और पानी उड़ाएंगे तो पानी जब तक रहेगा तब तक एक्सरे डिफ्रैक्शन नहीं होगा. So particularly it is useful when you have to do something with solvent. Then diffraction studies with solvent, neutron is very helpful, neutron diffraction. So disadvantage is that sources are weak. Sorry, VAWEAK, spelling mistake is there. Sources are weak. Signal, low signals. Need for you need large samples because it is almost neutron goes through unhindered most of the time, and you cannot do often because centralized facility. It is a centralized facility and very expensive. Some elements like cadmium, boron, and gadolinium absorb strongly, so it is difficult to do their study their structure. Absorption in more prominent absorption of the nucleus. They capture the nucleus strongly, and so scattering is not prominent, and so you can't study their structure, any compound of cadmium, boron, gadolinium. But all the and then you might have a range of energies for neutrons, but all cannot be accessed for this kind of studies. So those are some design problems in this thing. So and then there's also electron diffractions. uh, yeah, this is an example of electron diffraction. So electron beam, I didn't talk about much about the electron diffraction because it was most of the time similar to X-ray diffraction. So if you have a, instead of X-ray, if you use a beam of electrons, they can also, they have the wavelength uh, of around 1 to 3 angstrom, and that is, so you satisfy the criteria for diffraction because separation between the atoms in a crystal is also of the same order. So this is a typical example just how the electron diffraction pattern looks like. So you can see this electron diffraction pattern. So ring like structure. So this is the bright fringes that you see corresponding to different lattices, and this is done by me. This electron diffraction pattern is none other than, it's yours truly. Yeah, it's me. So it was done by me when I was in National Institute of Singapore. So this kind of thing is commonly used. Electron diffraction is also a technique that is used commonly. You need to have a source of electron beam, and then it can be done. So sometimes it is useful because the requirement of sample is very very less. Just a drop of that, make it dry, and then you can easily get the diffraction pattern. For X-ray diffraction you need a large amount. So every technique has certain advantage, disadvantage. But electrons, as expected, as shown in previous slide, the penetration depth of the electrons will be less because it will be easily scattered, because of the because of the repulsion from the electron cloud of the atoms. It will be repelled, and so that will, penetration depth will be low. So multi-layer structures cannot be well understood if you have you cannot understand many things about that if you are using electron diffraction. So if I summarize whole thing here, so this is a pictorial summary of the diffraction techniques. So red one is the nuclear so this is the neutron. Red one is the neutron beam. So a neutron travels through this. It, most of it, the interaction, it is scattered. It is passes through unhindered, and only gets scattered when you have, it strikes a it meets the nucleus and then gets scattered. So this is the scattering of nu- neutron. But if you think that if suppose one of the atoms is having unpaired electron, so this is the unpaired electron, so it will generate a magnetic field. It has some magnetic moment. It will generate a magnetic field of its own. So this magnetic field is shown over here, north to south direction. So this is the tiny magnet. So this is a electron, unpaired electron is present, electron. And if, so this neutron is going through like this, but when it reaches here, it is in the magnetic field. It feels the, it is a through space interaction. See, it is in the now field. It is closer to the electron, and so gets deflected. This is the magnetic scattering. This is example of magnetic scattering. So when it passes through a center, an atomic center which has unpaired electron, so that unpaired electron has a magnetic field. So that will, so it will the neutron itself is behaving as a tiny magnet. So you see here picture, this arrow is to denote the magnetic moment of the neutron. So it is a magnet, two magnets, like two small magnets are interacting, so it is getting scattered from here. So in this manner you are able to know, so this is a interaction of two magnetic dipoles, interaction of two dipoles, magnetic dipoles. So that interaction leads to scattering. So this is, there are two mechanisms by which neutron is scattered, and this is only in case of magnetic materials where unpaired electron is present. So neutron has magnetic moment, that's the thing, and that's why we are able to get to learn about this magnetic properties. In contrast, if you have X-rays, there's only one thing, it is getting scattered by the electrons present over there, and it is the electromagnetic interaction that you see here. If you use electrons only, then electron beam will be only so. So this is the thing. So we have X-rays, electrons beam with yellow lines that we, sorry, electron beams with yellow color. अरे कहाँ गया इसमें? सॉरी, ओके, साइज थोड़ा बड़ा है इसलिए इसमें दिख नहीं रहा, कट गया था. सो एक्चुअली दिस इज द समरी ऑफ, मैंने जूम इन किया था और थोड़ा सा कट गया था, बट इफ यू सी दिस, so in contrast, if you have this electron beam, it will be scattered even less. So depth, so what is it showing? The picture summarizes many things. It is showing a very long distance for the neutrons, so that is the penetration depth of penetration is high. You see, follow the X-ray, it is getting scattered from this point, so penetration depth is low. So relative order of penetration through a layer of atoms, that is being shown over here. And electrons have the least penetrating electron beam, if you have, that will be least penetrating. So this is the yellow curve, this is the electrostatic. So electron is scattered by electrostatic interaction, X-rays are scattered by electromagnetic interaction, neutrons are getting scattered by two modes. One is the nuclear interaction, when a neutron strikes another nucleus, it gets hit and so scattered. And then it can also get scattered by magnetic interaction with the unpaired electron, and that is, so it has, so one is magnetic interaction, another is nuclear interaction, both are the two modes. And neutron has the maximum penetration depth. So this summarizes the whole thing. So X-rays interaction is electromagnetic in nature, for electron beam it is electrostatic in nature, and for, if you talk of neutrons, it can interact in nuclear forces, so through nuclear short range force, and it can also interact through magnetic moments of the unpaired electron. So dipole interaction takes place, and so you get all. So this is the summary of diffraction techniques. That's all for we have. That's all I have here in this semester for X-ray diffraction. So there's also tabular comparisons for the wavelengths range, 0.4 to 10 angstrom for neutrons. In X-rays, 0.1 to 5 angstrom. This is the range. Electrons you can get from this to 0.04 to zero point 0.2 angstrom. Energy ranges in this, energy ranges in this EV. So neutrons of low energy you can use and get a very good diffraction pattern. So diffraction, and then you are also getting magnetic magnetic structure, crystal structure for phonons, spin waves, it is good to study the magnetic excitations, spin orbit coupling, all these things. So neutron diffraction is very very good, but it is limited to uh, it is you need a nuclear reactor usually, and that is difficult to get. It is a one like a national level. You might have one facility or two like that. X-rays we have already studied a lot of things. So typical. So what is the advantage of neutrons? Any bulk sample, any sample you can put and you can get the idea. But with X-rays you need to have crystalline powdered samples only. Electron beam can analyze thin film surfaces, grains of gas, and like this. So that's the final conclusion. And yes, so for the instrumental techniques part, we are finished. From my side, it's done. You need to focus on, as I told you in in the starting of the class, on the HKL values, the D diffractions. So you can check the assignments that I have given, even whether you are doing or not. You just go through this. एक बार देख लो, एक नज़र डाल लो, ठीक है ना? एक्सरेज आपका नेट में भी आता है, एक्सरे डिफ्रैक्शन. सो कुछ कि ये तो हमारा है नहीं, हम क्यों पढ़ें, ऐसा मत सोचिए. पढ़ना चाहिए आपको भी. हमने तो ये टॉपिक लिया नहीं है, सॉलिड स्टेट नहीं लिया है, तो चलिए कोई बात नहीं, उसमें कोई बात नहीं है, लेकिन पढ़ना चाहिए. ठीक है, ओके, थैंक यू. मिलर इंडिसेस का क्वेश्चन आता है हर बार, ध्यान से दीजिएगा.